Now consider this example. In this example, we have two double bonds, and in this particular double bonds we have even number of double bonds. Just see the terminal valencies which are attached with this alkene. You will get to know we have even double bonds and terminal alkenes are perpendicular to each other. We have two hydrogens. We have here one hydrogen and one chlorine. So these are terminal valencies, and the terminal valencies are always perpendicular to each other in the case of even double bonds. Then you have to check that if these two valencies are perpendicular to each other, then how many number of planes are passing from this particular molecule. You will be get to know if you are going to pass a plane here, your two hydrogens on left hand side will get reflect, and if the hydrogens reflect, it means one plane of symmetry is there. One plane of symmetry possibility is there, and it will be existing in this particular molecule. Now consider on right hand side, you cannot pass a plane like this. You cannot pass the plane like this in which these all particular atoms got bisected, and you have to pass the plane like this because hydrogen and chlorine got reflected. But this is not possible because hydrogen will never reflect chlorine and they are perpendicular to each other. So they have only one plane of symmetry in this particular molecule. And the scenario of COS, I have already told you that you don't have to consider the parameter of center of symmetry in alkenes having even number of double bonds. Never see the concept of alkenes for even number of double bonds. I give you a suggestion to solve the question in the exams. You have to consider only plane of symmetry, and from that you are able to get either the molecule is optically active or inactive. So due to the presence of one plane of symmetry, you can say that this particular compound is optically inactive because there is a one plane of symmetry, and if there is one plane of symmetry, then this particular compound is optically inactive. Hence this is the example of optically inactive alkenes. Now consider this example in which I am having hydrogen and chlorine on both the sides. Hydrogen and chlorine on both the sides. This is again the example of even number of double bonds, and if I have even number of double bonds in this particular alkene, then the terminal valencies are perpendicular. If I am saying terminal valencies are perpendicular, it means that hydrogen is perpendicular to C because terminal valencies are perpendicular. Now consider there is any plane, any COS. So COS criteria we have to neglect because this is the case of even number of double bonds. If we have two double bonds, that is even double bonds in alkene, then we don't have to consider the case of COS because we don't have to see the center of symmetry. Now consider the criteria for plane of symmetry. There is no plane of symmetry. Why? Because if I am saying I am going to pass a plane like this, you can pass this plane? No, because it's not possible because hydrogen is going to reflect here and this is not possible. If I am saying I am going to pass a plane like this, then also the plane of symmetry is not exist because hydrogen will never reflect this here. Hence this is the example of optically active alkene. This is the example of optically active alkene. This is very important example. You have to consider some example and set your own reference. Just for one particular example, if you are going to set your own reference, by seeing that particular reference or standard in your mind, you can solve the question in your exams very easily. That's why I am adding questions to get your understanding of particular concepts easier. So please mention this if you're going to understand, or if you are going to memorize even any example, you can set that standard in your mind and solve the respective question that is asked you in the exams. Now consider this question. In this particular question, you are having a alkene on which there is hydrogen on the terminal ones. This is again the example of even number of double bonds. Even number of double bonds are present in this particular alkene, so that's why the terminal valencies are perpendicular. Terminal valencies are perpendicular. Then I must say, but it's an exceptional case in organic chemistry. You have to memorize this particular example. You have to consider this particular example. If in any alkene you are having this type of a group, this is a chiral group. Why I am saying this is a chiral group? Because the carbon is chiral center. This carbon is chiral center. Why this carbon is chiral center? Because from this particular carbon, 4 different groups are attached. This is a chiral center because 4 different groups are attached. If 4 different groups are attached to this particular center, one is hydrogen, other is deuterium, tritium, and this particular group, then if the 4 different groups are attached, then this particular center is known as chiral center. Now consider the plane of symmetry in this particular group, because I am saying we have 4 different groups, so we have a chiral center in this compound, and if the 4 different groups attach with a particular carbon, the center is chiral, and if the chiral group is there in alene, then that alene is optically active because of the presence of the chiral center. Just because of the presence of this particular chiral center, your alkene, this particular 2 double bonds are optically active. This is a chiral center, and due to the presence of this particular chiral center, this particular alene is optically active. Because of the presence of this chiral center, irrespective of POS and COS. Irrespective of POS and COS, you have to check the chiral center. Please mention this question as very important, because this question involves 2 concepts. So once the concept of the chiral center in optically active compound, and you know how to check the optical activity and inactivity by putting your symmetry elements aside. So you have to check that. Next question is, when you are having a odd number of double bonds. When you are having the odd number of double bonds, then this is the alene which is having odd number of double bonds 1, 2 and 3. So you have odd number of double bonds, and when you have the odd number of double bonds, then your terminal valencies are planar. What does this mean? It's a very easiest one to solve. Just consider this is the odd. So how I'm saying your terminal valencies are planar, it means any number of carbons then come in between these terminal valencies, put that carbon as 0. This is the very shorter way to solve these types of the questions. So as when you are having the odd number of double bonds, then the terminal valencies are planar. So just consider these valencies as this, and consider any number of carbons are there. If you have 10 number of carbons, you can just put a single double bond and solve your question. Either POS exists or COS exists, as you are going to solve in the case of alkenes. That's it. You just have to do this, and from that you can get your answer, either it's optically active or inactive. It's the easiest way, because these valencies got planar, and when these valencies got planar, then they all exist in a single plane. And when these valencies exist in the single plane, then there is always a one bisecting plane that exists in all alkenes. And this particular alene solved by forming a particular alkene. So that's why there is one bisecting plane that always exists in the odd number of alkenes. Always mention this point in your notes as well, that when you are having a odd number of double bonds, then the terminal valencies are planar in nature. And when the terminal valencies are planar in nature, it means these particular four atoms occupy in one plane, these 4 atoms coming in one plane, and when these 4 particular atoms are coming in one plane, then there is always a bisecting plane. That's why odd number of alenes are always optically inactive. You have to remember this. This is the very important question of alenes, optical activity of alenes. So you have always one bisecting plane, and the concept of the COS, you don't need to see that. Although you can see the COS is odd number of alkene as well, because just consider a center here, hydrogen on this side, hydrogen on this side, chlorine on this side, and hydrogen on this side. And if you have different environment, then the center of symmetry will not exist on this particular point. So just consider this particular inversion center and check, because there is no same environment, so there is no COS. But the POS will always exist. Plane of symmetry will always exist in the example of odd number of alenes. Now consider this is the very important diagram which I've already explained you, but you have to check what's the basic scientific reason behind the formation of the perpendicular planes. So the pi bonds are generally formed. Just consider this is the pi bond, this is the pi bond, this is the structure of alene which is drawn like this. This is the structure of alene which is drawn like this, and you have to mentions the valencies. So there are 2 hydrogen on this side, and there is 1 hydrogen is above the plane and 1 hydrogen is below the plane, like this. 1 hydrogen is above the plane and another hydrogen is below the plane. So now consider the pi bond. So this is a particular pi bond. I am saying just consider this is the px pi bond and this is the px pi bond, and when these px pi bonds overlapping, these px orbitals overlapping, a pi bond is formed. But just consider this is the py bond and this is the py bond and this is the perpendicular, because this is the pi bond which is formed by the overlapping of px orbitals, and this is the pi bond which is usually formed by the overlappings of py orbital. So what you have to consider, each carbon is sp2 hybrid. Always, it's a very important thing in allenes. This is sp2 hybridized, this is sp2 hybridized, but this carbon is sp hybridized. You have to learn this, because in question sometimes the hybridization concept is usually raised, like the middle carbon of the allenes is sp hybridized because this particular carbon is forming 2 pi bonds, and if a carbon is forming 2 pi bonds, then the hybridization of that particular carbon is sp hybridized. So you have to consider this particular example just to have to learn the hybridization of the carbon atoms. So when you are having the carbon atoms, this is sp hybridized and this is sp hybridized because it's having a 2 pi bonds. Now consider this particular carbon, this particular carbon, this. So there is px orbital and there is px orbital, and that sideways overlapping of px orbital leads to the formation of pi bond, and this particular overlapping of the pi bonds leads to the formation of pi bonds. So when the py molecular orbitals overlaps, then a pi bond is formed. So these 2 pi bonds are forming in different directions. So the pi bonds formed as a result of the overlapping of p orbitals, so that must be right angles to each other. So this particular plane, when these two molecular orbitals getting overlapping, sideways overlapping, this particular plane arises. But when this particular orbitals overlapping, this particular plane will exist. So these 2 planes are perpendicular to each other. I have already explained you how the 2 planes are perpendicular to each other like this. Then these 2 planes are perpendicular to each other. Not only 2 pi bonds are perpendicular, 2 methylene groups are perpendicular as well. So just consider an example of allene, that is if I am drawing allene like this. So if I am saying there is 2 CH3 group that is attached to the allenes, so if I am saying these 2 CH3 groups, suppose there is a bromine group and there is a methyl group, then they also perpendicular to each other, because this is an example of even allene. They are also perpendicular to each other. So you have to careful, not like which group is attached to allene. You have to recognize the main characteristic group of the organic chemistry, and then you have to solve your question. Then you have to solve your question by seeing a standard structure which is present in the question, and you have to first recognize that and solve the question accordingly.